That's really what we're going to be talking about today, and specifically how we strengthen that to give us something that we want. So in essence, that's what we're going to be talking about today. And you will see why we call it permeation engineering. That's myself, David Kitching. I'm the managing director and the co-inventor of the ReFORCE system. So I'm managing director of the stress group, and my colleague and I, Simon Collis, invented this system of injecting into the ground, and you'll see why it's different if you know anything about it. And that's one of the things I normally do to a live audience is I'll say to them, okay guys, who's got experience of polymer injection into the ground, used it, seen it, specified it, whatever. And it's surprising how few people have, but there are always people who've either got some comment on it, and certainly some very good questions too. So I'm hoping that we'll get some interesting questions at the end of the day, which, as Matt said, you can either write in, or if there's time at the end, obviously, pipe up, and I'll do my best to answer those questions. Just a little bit about the stress group. I started it 30 years ago, or just over 30 years ago, as structural repairs and specialist services, and we basically repair everything from bridges to tunnels and houses and commercial buildings and anything. And within the group, then we've always got the geotechnical side of things, because I'm a geotechnical engineer and I always love keeping my hand on that, to doing traditional underpinning and some specialist piling. But we also do quite a lot of other things, including heritage engineering. So we get involved in a lot of old buildings, and we have our own conservator. So it means that we can talk to conservation officers on a fairly equal footing, and help a client out with some of these old buildings. And these can go from old bridges to monuments and things like that. Due Innovations is our intellectual rights company. Simon and I own that, and we look to invent different methods of strengthening the ground, altering it for the purposes of the industry. And so we patent whatever we've got, and then we'll license it back to, in this case, we license it back to our own company to use. And that's been great for the last 18 years. It's worked extremely well. But the other company that you see there, Goldhawk, this is a bridge restoration company, so it ties in incredibly well with the sort of work that we do in the group. We specialise in masonry arch strengthening, everywhere from under pavement vaults right the way up to network rail bridges. And we're doing one in Cardiff at the moment. And we've been working all around the country with various local authorities and highways department, strengthening some historic, some not, but mainly fairly historic masonry arches. So that's us. You can see we're sort of, you can see why innovation kind of creeps into our company, because we're always looking for new ways of doing things, trying to improve, reduce carbon footprint, etc., etc. So today I'm going to try and demystify polymer grout injection. So what are we trying to achieve is one of the questions that we're going to answer. What's the science behind it? It's got to be a science behind it. You can't just point and squirt. How are we going to make sure it works? Because that's the other thing. You can tell people it's worked, but how are we going to make sure it has worked? And the key question here, which I really want you to keep in mind, and I'll try and remind you as we go through it, is what type of soils does it not work in? And this is where people are getting the wool pulled over their eyes at the moment, which is rather annoying. And my computer's decided to, sorry about that, for some reason the keyboard decided to take a break. Permeation ground engineering definition. It's the science of forming an in situ solid composite mass using a setting fluid, a resin, grout, to bind the soil particles together. Okay, seems fairly straightforward. And obviously the purpose of that is to strengthen the ground so that you've got a greater bearing capacity. It's pretty simple. So the task, therefore, is pretty simple too. We just need to deliver that fluid, this ideal magic fluid, exactly where you want it and in the quantities you want it. So that really is all we need to do. But we're going to show you how that's not quite as straightforward as you would imagine. So first of all, let's think of fluid. So we're going to take you back to your physics days at school, or if you went on doing fluid dynamics at university, then you will know all about this. But fluids do behave differently, and if you put a fluid under pressure, it will always try and escape to the point of least pressure. So your garden hose, for instance, it's got a hole in it. The water's under pressure in there, probably 2 to 3 bar, depending on what sort of water pressure you've got at home. When there's a hole, it will just escape to the atmosphere and you'll get a nice fountain coming out of it, or leaking connections, all the bits and pieces. Again, think fluids. They just want to get where's least pressure. Okay, so bear that in mind too. And we're going to compare two types of fluid for this injection process. One is a Newtonian fluid, which you may never have heard of before, but basically it's things like water, gin, whiskey, wine, olive oil, certainly, oil that you put in your car, petrol, anything that's got no solids in it. And we're going to compare that to a particulate fluid, things like a cement grout or a bentonite grout, things that are very common in the civil engineering world for all sorts of reasons. So to demonstrate this, we've got two types of soil here. On the left, you've got a fine soil, fairly uniform fine soil, a bit finer than you would find on a beach, but not dissimilar. On the right, you've got probably the most permeable soil on the planet, a mixture of sand and gravel. Okay, and we're going to first of all pour a Newtonian fluid into that. And I think what you will see here is what in your mind you understand as permeation. So under no pressure at all, just gravity feed, capillary action, that fluid, that Newtonian fluid, is actually just flooding between the particles. Okay. And that is the process that we want for our permeation engineering, our ground stabilization, because we're binding all the particles between the fluid. Okay. Look what happens when we try and use a particulate fluid. Similar viscosity, as you can see on the left there, into the sand, probably doesn't even go in a millimeter. On the right, probably average about 50% of the way in. And the reason for that is that particles, as they are forced between the soil particles or the platelets, so you've got in the cement, all suspended in the solution, they will try and move their way between the particles, but they jam up between the soil particles. They jam up, and then the next one comes up behind that and jams, and the next one comes up and jams and jams. And as you can see there, you've not even gone in a millimeter into that sand. So you can force it in by increasing the pressure. But what happens is you build up that filter layer and it gets stronger, and you keep increasing the pressure until the soil just shears, and you will end up with what's called hydraulic fracture. And that grout will just disappear through the soil in a series of sort of legs, um, little sort of lightning bolts through the soil, but you've got no control over where it's gone. It has just legged it into the soil. And so this is the problem with using a particulate fluid, a lovely cheap cement grout. And we can see it here. So on a pressure distance curve, you will see with Portland cement there, it goes so far under a certain amount of pressure, stops. That's as far as it'll go until you increase the pressure. If you use a microfine cement, it will go a little bit further for the obvious reasons. The particles are that much smaller. They will actually get between the soil particles a little bit further. But if you think that that white fluid that we were using was actually a microfine cement, it gives you some idea of just how little penetration you're going to get. If you use a Newtonian fluid, however, there's none of those particles clogging up the pores. It just nicely soaks into the soil. And the more pressure you put it into, the quicker it will go into it, in theory. But ideally, you keep the pressure low and you allow it just to soak into the area of soil that you want. If you use a resin that we're going to use, which is the sort of geotechnical grout that we need, because we need this thing to flow into the ground and then set so that it binds all the soil particles together, then you need something like this. We developed this with Normet. Used to be a company called TAM, and they had various polyurethane resins, hydroreactive ones that we tried in our first experimentation to see what sort of reaction we'd get in the ground. And we realized that something called TAM PUR125 was actually not too bad. But there were a number of things. It was too expensive, it wasn't low enough viscosity, and we couldn't sort of control the reaction time well enough. And so, in fact, we work with Normet. They produce something that works, and Geotech LV is available on the market for anybody to buy if they need it. But this is the material that we use for consolidation. Now, when you use something like that, as you can see, it follows the same sort of curve as sodium silicate that we used on the red line, but it slows off slightly more because it's slightly more viscous, and then it starts to react with the water in the soil, and that sets off the reaction. And what happens is it generates tiny little bubbles of microfine bubbles of CO2, and that has two effects. One, it reduces its viscosity, so it flows more easily through the soil. And the other thing is that it actually just gently expands too. So from every center around, it's just gently pushing its way through the soil. So you will go from something like that, which you can see is just a loose soil, and you will end up with that. Okay, so I hope you can hear that. That's pretty hard. And that's taken out the ground. That is a piece taken. It's not a piece taken out the lab. That came out the ground, and I'll tell you about the job as we go through. So, obviously, permeability is what it's all about, which is why we call it permeation engineering. Now, probably some of you around the table have got mugs of coffee there. We make mugs out of clay. Because it's malleable, obviously. And yes, they get glazed for hygiene and longevity. But in essence, you could just throw a clay pot, pour some water into it, and it would hold the fluid. So actually, it's not very permeable. So clays are not ideal for grouting. Okay, there are companies that will tell you they are. They aren't. And then you will see as you come right through to those gravels on the green end, like our sample you saw in the jar, that's where you get most permeability. So you've got to look at the soil from a site investigation and decide whether you think you're going to be able to permeate it correctly. Okay. So what do we sort of get when we grout the ground? Here's one of the experiments that we did early on, and you will actually see you get this fairly healthy lump of material that's combined. This is it around the lance. And one of the things that we'll tell you about later is if you it's the bond that you get between the steel, between that injection tube and that composite material is really quite phenomenal. Now, we did the same experiment as you can see on the left in clay. Nothing. You don't really get any permeation to it. It probably got into some of the siltier fractions, but that's basically all you get. So it's not done anything at all. So it was a pointless exercise. So it seems pretty simple, doesn't it? Now you just put a tube in the ground and squirt some resin in it. Why invent a new system? Well, we do a lot of insurance work and we have done over the years. And going back, that's about 20 years, I would think, a new injection system came along. We thought, that's interesting. So we got permission from one of our insurance companies to use it on one of the jobs that we had up in High Wycombe. That's not far from where we are here in Slough. And I thought I'd go along, geotechnical engineer, head of the company, better go and find out what all the fuss is about. So I turned up at this property and it was simple. It was going to be the injection of 2 meter deep fill under the conservatory slab that had settled. So I met the guy down there, technician. He got a nice van, and I said, "What are you going to do?" And so he said, "Well, I'm going to drill 25 mil diameter holes, and I want you to think about these parameters that I'm going to give you in a minute, and just see what you think about this. Remember, fluids do what they want to do." So he's going to come along and he's going to drill 25 mil diameter holes through the slab at 1 meter centers. He's then going to take a 25 mil drill bit, 1.5 meters long, and he's going to drill down into the fill, pull the bit out, go on to the next one, go on to the next one. So he's created 1.5 meter long, 25 mil diameter holes. So what are you going to do then? He said, well, I'm actually going to go and get some copper tube, 15 mil. I'm going to drop it into each of those holes. Then I'll resin up between that and the slab, stop the resin coming out. I said, oh, okay, fine, excellent. I said, well, then what are you going to do? And he said, well, I'm going to go and have a cup of tea while the resin goes off. So I stood by and waited for him to come back, and he came back through with these 3 heated lines. So it's all this heated resin. It comes in 3 parts, mixed at the nozzle, and he links it up to each individual copper tube. So I said, fine, great. So how much are you going to put in each one? And he said, loads. So I said, don't you know exactly how much you're going to put in each one? Is it how many liters? No, we're just told to put absolutely loads in, as much as we can get in. I get a feedback, So I said, okay, fine. I didn't tell him I was the client, and off he went. Now he'd done about 3, and he'd got loads into 1 and 2, and he was on the 3rd one when there was a knock at the door. So I went there because there's nobody else in the house other than us, and there was a very irate lady. And she said, are you working here? So I said, yes, we are. She said, well, something's happening next door, and I don't know if it's something to do with you. And so I told the technician to stop. I went next door. I said, what's happening? She said, well, I was in the kitchen and suddenly noticed that my washing machine was moving across the kitchen floor. So I said, okay, things starting to, alarm bells starting to ring. And by the time we actually got to her kitchen, which was only a matter of minutes, not only was that you could see that the washing machine had moved out, but that the wall units were starting to bulge off the wall. So I said, look, we better get out. Here's my card. Here's all my details. This will all get sorted out without any delay. It's definitely something to do with what we're doing. Really sorry. Went back, told the technician to pack up, go back, tell him his office what had happened, and organised to get back and sort this lady's house out. So I sat in the car, as you might, thinking, what the heck happened there? And I thought about it, and it soon became apparent. Let's go back through what he did. He drilled a 25 mil diameter hole, and he put a 15 mil copper tube in it. So that's got a 5 mil annulus all the way around the outside. What do we say about fluids under pressure? They will always escape to the point of least pressure. Where's that? Straight up the side of his copper pipe, out under the slab. What nobody knew, we blocked the drains. What nobody knew was that when the builder had built these detached houses, he'd run a duct along, and it went down the back of the house. Obviously, there's a conservatory on top of this one. Probably for running cables or something like that. We don't know. But the resin came up under the slab, found this duct, shot along the duct. Nearest place was next door. There was a gap in this duct somewhere under the footing. It went straight up into the cavity of next door's house, and then started to react. Of course, it expanded, pushed all the block work off on the inside. So what have we learned here? Well, first of all, that fluids will go where they want to, not where you want them to go. They will go just where they want to do, where's easiest. And the second is that you've got to create something that confines that resin to where you want it. So we had to invent a new system. So we thought, I know what we'll do. We'll get a nice piece of steel, and we'll drill holes all the way through it. The one as you see in the diagram, and we'll drive it into the ground. So we'll smash this into the ground to the depth we want, 2.5, 3 meters, and then we can inject the resin from there. And the beauty of driving it means the ground is tight around the lance. Okay, so it's less likely to want to creep up the lance and out. There's no void there, but we want to discourage it. So what do? We did that. We put a packer in the top. We linked up the pump, and we started pumping to distribute resin throughout that lance. Any of you smarties know exactly what happened then? I think you can probably guess. What do the resin want to do? Come out the easiest place possible, just near the top. Comes out the first couple of holes, because once it starts getting deeper, it's more pressure down there, and it's harder. It's got to push against the soil. But up here, it's not really any resistance, so it just, of course, just flowed out the top, and we ended up with this strange carrot-shaped thing. So that wasn't the answer. We had to go back to the drawing board again. And so what you do now to force that resin where you want it to go is put valves in the lance. So the lance actually has a series of valves in it. Here actually is a blue piece of one. You can see the valves there. You can see the delivery tube in the middle, hopefully. And what you then do is distribute the resin into the individual chambers in the quantities that you want, not loads, quantities you want. And then you pull the tube up and deliver. So this is kind of what happens here. So first of all, it goes into that chamber. It can't come out in the next one because the injection tube is blocking it. So it just comes out. Now, the easiest thing for that resin to do, it doesn't want to go all the way 2 meters to the surface, just go sideways. We only want it to go 125 millimeters, and then it will start to react, and then it will expand out to about 0.5 meter diameter. So it's easy. That resin will only go where we want it to. And you put these valves in at 0.5 meter centers. So it expands. The delivery you want, you pull the delivery tube up into the next chamber, the valve shuts. So when you then gently pressurize that chamber, it only comes out of that one, and so on. So if we're looking to underpin a house, which is what we do most commonly, you expose the top of the footing, which obviously is nice and shallow. You drill a 40 mm hole in it, and you drive a 33 mm diameter lance. Now, I know you'll say, yeah, but there's a bit of an annulus between the footing and the lance, so resin's going to come out of that. Yeah, it would if we didn't put a gasket. So when we drive it to the depth we want, there's a gasket up here, and we drive that in, that packs out any gaps, stops the resin coming up to the surface. So we keep driving to the design depth, and we'll look into the design later on. There, we got it. Now, the graphics didn't work like this, but in fact, we drive these with a tube already in position and at the bottom. And then when we join on sections over the tube and then keep driving, that's the way you do it. Otherwise, you'd never get that tube past all the valves all the way down. And then you start injecting. So as we said before, you inject not loads, just what you want. And what you want is somewhere between 7.5 and 10 litres of resin per half metre of lance. That's all we ever deliver. So you've pulled the injection tube back and you start injecting in the next level. And you'll see that lower level, that first level we did, is starting the chemical reaction. And that blows out. So as we continue up to the underside of the footing, you've created a column of soil with that sort of characteristic. So you can quite happily sit a house on that. And that's the process. This is how we drive the lances. It's as simple as that. You can see we've exposed the top of the footing, drilled the 40 mm holes, and Jason here is now driving those lances to 3 meters depth with a road breaker. And that is the beauty of it. You can go anywhere. We can do it inside people's houses. And roughly as you saw from that photograph before, this is the sort of edifice that you're going to get. It's a roughly half-meter diameter. Sometimes it's bigger. You can see a bit lower down, it's flowed into a gravel layer a little more, and you end up with something big and rough and with a huge capacity. There's one we dragged out. It's held up on the lance. Remember me saying about the fact that it's got this phenomenal bond of steel lance to the composite material, and this is why we can't reuse the lances. So they're driven, they're sacrificial. Okay. Some people do, they pull their tubes back. They're using very fine tubes that they've put in a drill hole, and there's no friction, but they're only blowing resin out of the bottom of those, and basically it fills that tiny little hole that they've inserted. It doesn't go into the soil. There's no mechanism for it to do that. But here we can see that lance is well bonded to that part of the ReFORCE pile. And if you were underpinning a building, very roughly, that's what it would look like in graphic form. We pop these things in at roughly 1.2 meter centers, closing the spacing if you've got higher loads. But that's roughly what we got. So there's a little recap. You've created something about half a meter diameter. I say up to 14 meters or more. We've gone deeper than that. But economically, it's never going to work really much deeper than about 5 meters, unless you've got some really unusual circumstances. But we know we've driven them and formed them to 14 meters or not. We've extrapolated a loading of 800 kilonewtons based on testing that we have carried out. A 3.5 meter deep lance ReFORCE pile created and then tested to, well, basically to as far as we could take it. We used a 35-ton excavator, and we were starting to tip it back. Maximum we got to was just under 21 tons, and we didn't want to. There was no way of doing the test any higher than that, but we know it would have taken a hugely more capacity than that, because we got nearly no deflection at all. You've got that incredibly aggressive piece um, uh, of stiffened soil with all these nubbly bits on it, and it really resists being moved. So it doesn't like being pushed down into the ground. And you've done all that through a 40 mm diameter hole. So it's pretty effective. What are the advantages? Well, for those who get involved in underpinning, and we still do master concrete underpinning, you don't have to dig holes in the ground under a building. Put guys down there. Yes, we do it. We do it safely nowadays, but in general, it's still a risky thing to do. Put a guy down in the ground digging. Not a nice thing to do either, really. And if you don't dig a hole, you haven't got muck away costs. And if you haven't got a hole, you don't need to bring concrete to fill it. And we all know the carbon footprint of concrete's not ideal. So the less concrete you put in the ground, the better, basically. So it's got a huge number of advantages. It's fully engineered, so we can get a latent defects warranty on it. It's economical. Yes, in the right circumstances, as I said before. I mean, if you're going to go to 14 meters, there's no way you would bring a big piling rig on, CFA rig, and that would be the most costly way of doing that. But within certain boundaries where you're not going to be able to get one of those rigs in, you know, digging holes would be hugely disruptive. You can create incredibly high capacity piles in virtually no space with no disruption. And they're reliable, and I'll show you just how reliable they are a bit later on. So it's a graphic, but we've done it. We have actually done this from inside an understairs cupboard. We've actually put these in underfloor voids up in Newcastle upon Tyne, stabilising around an old lift access shaft to a mine. And that had to be done under a dental surgery's floor whilst the dental surgery remained in action. It was, yeah, it was interesting. As far as we know, this is the only patented, fully designed and guaranteed ground permeation system for anything, but we use it for underpinning, anchoring, jacking, and ground consolidation. The underpinning we've just seen in the graphics. Anchoring, you saw just how that material bonded to the steel. Now, we did a lot of testing earlier on. So Simon Collis, whose name you saw there, my colleague, he's a material engineer. So he got involved a lot in his early career with concrete testing, grout testing, that sort of thing. And you make those 150 or 6-inch cube molds, steel cube molds, oil them, put in the concrete, tamp it, off it goes for curing, test it. 12, whatever, up to 28 days later. Fine, you get the unconfined compressive strength of that concrete. So I said, so let's do the same. So we get an idea of just, you know, what this composite material, just how strong it is. So we set the molds up, we put shuttering oil around them, did what we had to do to get this material into it, and then let that cure. And then we couldn't get them apart. We had to smash them with a sledgehammer and then grind the surface of plate to get it smooth again so that we could reuse them. The bond was ridiculous. We tried it again with thick machine grease, smearing that all around the inside of the mold. Exactly the same thing happened again. So this material, it is inert, but it doesn't worry about petrochems or anything like that. It just adheres to steel, unprepared steel. So I mean, I don't know if you can see on this, you know, that's a shiny, fairly shiny bit of Steel, that's what we use. We don't need it to adhere to it, unless, of course, you wanted to do some anchoring. Now, if you used these lances in stainless steel with a screw fitting, and you punched 40 mil or drilled a 40 mil hole through a wall, and then drove these to the depth, injected the ground, you've suddenly got yourself a fairly, well, very potent anchor. So we did the testing on that, and we've done retaining walls with it too. But of course, the soil's got to be right behind the wall. So you do all that site investigation. Jacking. Now you've created this thing in the ground. It's got a huge capacity. We jacked that 35-ton excavator off the top of one of these things. So what if it was just under a slab and you put a lifting collar in? You'd be able to jack off the top of the lance and level the slab. So we can do that too. And it means you're doing it mechanically, not by a series of injection processes where you use an expanding grout to lift the slab, because it can go wrong and you overlift, then you're in trouble. So we have used it for jacking and for ground consolidation, and you will see, and that's what that sample came from. It's from one of our ground consolidation problems, which we'll take you through in a case history in a minute. But as I said, what was the design? Come back to the design. Anyway, while that's up there, we have a spreadsheet, and all we need from a site investigation is the type of soil and probably some grading curves, SPTN value with depth. That's it. That's how we design it. We design it very much on the style of a pile, reinforced concrete pile, and with skin friction and bearing, because we know how big they are, and obviously these quite a lot of these parameters are fairly conservative, because the concrete that we create, this composite material, is much rougher, got a much bigger skin friction than you would off a concrete pile. So again, sorry, I'm using a version that these aren't in the order that they're normally in, so maybe this might be Simon's. But so in fact, we'll come to that. We've excavated it and we know what this stuff looks like. So when we're doing a job, we take that site investigation and we mark on it exactly what depth we're going to go to, what zone we're going to grout, so that everybody can see it. Local authority, district surveyor, he has a look at it, because that gets passed off. It is classed as a pile, therefore it needs planning permission. Your technicians who are on site, they need to know exactly how deep they're going, what they're expecting to see and feel as they drive the lances in. You get a lot of feedback off how the ground is. Sometimes we've got to the depth at which we're supposed to be able to found, and basically you can push the lance in and it keeps going. So of course we keep driving as part of the experiment to find out where we're getting any end bearing. Oh, there it is. That's the sheet we use. Again, SPTN value, type of soil. You can therefore get some of the soil parameters, and we will do length, depth, end bearing, and skin friction to give a capacity, and then we put a factor of safety of 3 on that. Again, for the variabilities that you can get with soils. So one of the early ones was Boyne Hill House at Maidenhead, and this was all to do with a solution feature in HPC. We were working with, or we ended up working with one of the large housing developers who'd bought Boyne Hill House, which had a large area of ground onto which he could then put houses. part of the planning permission grant was that he had to put the old monastery back together and refurbish it, turn it into, I think, key worker housing in essence, but to improve the ground around in the actual grounds of the monastery, they use vibro replacement. For those who don't know, that is a very long, large, heavy poker that's vibrated into the ground, so densifying the ground, and then as you withdraw it, you feed in compacted rock, basically. So you end up with these stone columns onto which you can then put the footings. So you get a very, very high capacity footing. So off he went doing this. It was very wet. We've got alluvium over chalk at this part of Maidenhead, and the vibration and the amount of rainfall that we had at the time must have affected the plug in a solution feature, and it shook it out, and part of the old monastery was sitting on it. So that's what happened. You got these massive cracks occurred, and the builder then obviously braced these. We came in, had a look at the damage, and then tried to work out what on earth we were going to do. So the site investigation was to try and find the dimensions of the solution feature, and so we had a whole series of probes done by Card Geotechnics, and that's roughly the outline in plan of where we found the solution feature, very much like a molar. And we can see that the alluvium varied in capacity. So this is a cone penetrometer, and you can see it actually decreases with depth in some places. So we've got to be really careful how we design our footings. But once we'd worked out exactly where it was, and you can see that that sort of pink zone is the basement, and that was where we found that the basement was sitting over the center of the solution feature. The other areas have got different masses to them. The walls have got different load-bearing requirements, so we can extend the lances different lengths to cope for that. And in essence, that's what it looked like in cross section from our plotting. And we only need to take the lances down to the depth where we know we're going to get the capacity we require. You'll see there's a blue tube that runs down the middle. That represents a grout tube that we pop down there at the request of the developer. He wanted to see whether, rather than do all this, he could grout up that solution feature. So we got up to, I think it was just over 18 cubic meters of cement grout without the slightest feedback of pressure on the pump. You'll always get a feedback pressure on the pump when you're grouting. You know you're starting to fill the hole. So we realized you could go on like this forever, maybe grouting up an aquifer, because we're over chalk here, of course. Polluting a stream somewhere, you just don't know. So we stopped and went back to this scheme, the ReFORCE scheme, to actually hold up Priory. And at the end of the day, that was it, done. And because we're a structural repair company as well, we did all the necessary structural repairs to it. Very fine. This was, I think, about 13 years ago now. And as far as we know, we've never been called back. We think everything's absolutely fine with that. Now, some of you will have heard of a company called Abbey Pinford. We used to work with Abbey Pinford very closely. We're both asset contractors, or were asset contractors, Association of Underpinning Contractors. And they do certain things that we don't. We combined forces for various things. They did basements, we didn't. And they said, come and have a look at this. We've got a problem. So we went to Ennismore Gardens in Kensington, as you can see here, rather grand, tall houses. I think they're 5 stories, plus a basement, plus a mansard. So fairly heavily loaded uh, with a basement over terrace river gravels. Now that's fine, but the client wanted a 2-story basement beneath the existing basement, and that took them down into the water table, down onto the top of the London clay, which is where you want to be, actually. And so the problem was, from the site investigations that they'd got, they were going to end up trying to underpin in water-bearing terrace river gravels. You can't do it. As soon as you take a shovel out, and obviously the ground behind that area washes in, and you will end up with huge amounts of settlement and massive problems on this. So they knew about our system. They said, do you think it would work? So in fact, we got them to do some more site investigation, which actually at the end of the day saved them a lot of money. And we realized that we got the profile of the London clay with the sand and gravel above it. Now, for those of you who've dealt with basements, there are a number of ways of doing it. You can go inside an existing house and actually drill a series of secant piles down. Then inside that, you put a structural basement wall. But you've lost a huge thickness of the wall. You've got an increased thickness of wall down there, and you've lost a lot of the basement area. And of course, it's expensive. So real estate in anywhere like this is worth a lot of money. So every square meter you can save or gain, it's very, very valuable. And this client wanted us to follow the existing party wall line, so that his basement was as much as that. That meant traditional underpinning. So what we then had to do was come up with a system for holding back and consolidating this material below the party wall. So on the left, you will see our design drawing. And what we realized we could do was allow Abby Pinfords to build the first level of basement below the existing basement down to the top of the water table. And they put a toe on that, all in reinforced concrete, installed in an underpinning sequence. So you do the sequential underpinning, and it worked very well. We then came in and we drilled diamond core holes through at those specific angles, and we drove specific length lances to the depth so that you can create that area of consolidated soil. And that's what we did. First time we'd ever tried it. And we did that on the 3 sides of the basements that we needed to, because the London clay actually came up at the back of the house. So we didn't need to go all the way down and round a 4th side. And we then sat with the underpinners, who then broke off the toe where we'd done the injection work, and then dug under and trimmed off the material that we created. Now, I've been whacking this with a knife, and you get an idea of just how hard that is. Now, how hard is it? Well, we've done our tests, and that is somewhere between 3.5 and 5 newtons per millimeter squared. Now, for those of you who deal with concrete, that doesn't sound awfully strong. If we had a 25 Newton concrete, that's what 25 means. This is 3.5 to 5. But what you need to realize is that to support a house, let's say a 2-story house, you would need 0.25 of a Newton per millimeter squared of compressive strength. So this is 15 times stronger than we need it. Yes, it's a much taller house, but way in excess of what actually is required. So this material is perfectly capable of taking the loads it needs to. And the beauty of it is also that it stops the material washing from behind. You've blocked up all the pores, so water doesn't come through. So it means that these guys could actually trim this off. It's only 3.5 newtons, so you can actually use a breaker, just trim it off, use it as a back shutter, and then they don't need to line it. They just literally need to mop up any little bit of water that does come through, and a little bit came through, but nothing that would wash the fines from under the party wall and cause settlement. They ended up, I think this is about £250,000 to do this section of our work. They ended up 3 months ahead of schedule, and the client got a basement he wanted. So it meant that we could stand by and look at the stuff that we'd put in the ground blindly through holes driven to 3.5 meters or so. We could see it. We could see that it had been done. So in fact, it gave us that reliability. We then got asked by a company called Erith. I think you'll probably know Erith, a large civil engineering contractor, to help them with a new build basement, open ground, as you can see. At the back of the Dorchester, it was for the Dorchester apartments. They had a problem. That building you see there is a 7-story listed building, and it sits on about 1 meter of concrete on the top of terrace river gravels. Terrace river gravels, basically, it's like a bag of ballast you get from Travis Perkins. That's its consistency when it's unconfined. So when they realized that they were going to have to dig out below the existing footing to create the capping beam, they had a problem. So they asked us if we could consolidate the material under the party wall or under this flank wall of the listed building to strengthen it and stabilize it and take out any risk of settlement. So we said we can. We designed how to do it, but we said you cannot take out more than 2 meter length of that capping beam at any one time, and do it as you would do underpinning on a hit and miss basis, so that you limit that the main stresses coming down through the footing onto that, in essence, a fairly weak material when it's unconfined. When it's confined, it's perfectly capable of taking enormous loads, you can see there. So off we went. We got about 3/4 of the way through the job, everything going well, and we came in on a Monday morning, and a very helpful, or he thought he was being helpful, machine driver had got in on the Saturday and had taken out a 15-meter length of the trench for the capping beam. That's part of it there, below the footing. So there we've got that 7-story listed building sitting on gravel, basically, except fortunately we'd treated it. And it stood there, as you can see, not 1 millimeter of settlement. So they quickly backfilled it in a massive panic and then proceeded to do the hit and miss style. This was temporary works. This wasn't permanent. So there's no way we were going to let them drag the whole thing out. But it gives you an idea of the reliability that we've got with this material and this technique, to giving us something that we know we can rely on to support the building. Now here's another quite interesting use. Remember me talking about Goldhawk? We strengthen bridges. Here's one which actually is a Brunel bridge, and it's west of Reading. And Network Rail came to us and said, we've got a problem with this bridge. It is very lively. Now, I don't know if any of you have ever gone when you've walked under a canal bridge and you've been able to put your hands up under onto the arch, just feel whether you can feel any traffic going over. Very rarely you can feel anything more than a slight bit of vibration. Well, when we went to look at this, when a freight train went over, you could see the brickwork ripple. It literally, you just saw it ripple. So they did have a major problem. we measured the deflection at about 10 millimeters of the crown of that arch. So as the train went over, it deflected like that. A Network Rail wanted us to use our Mars system, our masonry arch strengthening system, to strengthen it and take out this bounce. We said there's a big problem with that. The reason that you do the Mars system is it allows the arch to remain flexible. It will increase the stiffness response slightly, but not enough for this. But we do have a technique that we think might work. And so we gave them Network Rail, we went and saw them and we gave them this seminar, and they said, yeah, we like that. I said, well, you need to tell me what the soil is, the fill over the haunches of the arch, because if we can't permeate it, it's not going to work. So they caught it, they found out it was sand. It was a sand fill that had been put over there. So you can imagine when you've got an arch and it deflects in the middle, it pushes out. So the arch actually tries to push out. So if you can increase the resistance, the lateral resistance of that ground around that arch, it will stiffen it. So that was the theory. And basically we designed it, went through all the hoops and everything you need to do with Network Rail for those who've worked with them. And off we went. That was the dynamic response of a freight train before we started. We actually only measured about 6 millimeters of vertical movement. Still frightening for a bridge. And then we went in with the ReFORCE system that's on the right. So that was the pattern. And you will see something very similar to you saw Ennismore Gardens where we were going under the party wall. It's a zone. You're creating stiffness in a zone. For this reason, to try and give that arch some resistance, some lateral resistance. Network Rail liked this because they knew that we would control where the resin went. Remember, I was talking about it only goes 125 mil from the lance. It then expands and will go double that, but it won't go any further. So they know they're not going to contaminate the track bed, which is a major problem, or create a hard spot. Again, another no-no for the railways. So they knew we could do that, and off we went. You can see all the holes that we did there. Mars system is that you can see on the left. So Mars system, so we installed it afterwards, and we set to. Normally we don't prop arches. Propping arches is not a good thing to do. You create a hinge point. So when the arch deflects, if there's a prop there, it will crack around that prop. So in fact, you ought to let the arch deflect and it then spreads the load around it. So in fact, we put maybe props in with 25 mil gaskets to allow the arch to move. But if there'd been a catastrophic failure, it would at least have given our guys time to get out to safety. So it was a pure safety thing. There we have it. And you can see the targets for measuring deflection because we measured throughout the process. So we're drilling top left to depth and the exact angle that we're supposed to go in at. We then drive the lances and connect up the pumps and pump exactly the right amount of resin per meter of lance. Lances varied in length, so we know exactly how much resin to put in. And we didn't get any leakage apart from that sort of little bit of leakage you see there. We didn't get it coming out anywhere, and that was all monitored. And within a few hours of us completing that, at the same scale, that was now the deflection of the crown of the arch. It had 2/3 been reduced. So we knew we were onto a pretty good thing, and we had a good idea that the Mars system would then stiffen it enough to take it to where they need it. That's the mast system. We can do another whole seminar on this for those who would like it. Um, it's stainless steel masonry arch reinforcement that we put into the underside of it, as you can see here. By the time we'd finished, yeah, I mean, generally you were getting less than 0.5 millimeter of deflection and around about 1.5 millimeters when the actual engine itself went over the bogies of the engine. Now, this gave Network Rail their route availability 10 category, which brought it up to both speed, load, and traffic volume. And they didn't have to shut the railway or take one train out of timetable. So they were extremely happy. And as I said, we're doing one down in Cardiff at the moment. And that's what it looked like at the end of the day. So you can see different uses. But in essence, what we use it most for is for stabilizing the foundations under a house that's suffered from settlement. So if that house sits on clay, no, you cannot use an injection process. No matter who tells you can, you can't. But where you've got permeable soils, this works an absolute treat. Thank you. Thank you for listening. I hope that was, well, interesting. What have we got, Matt? Have we got any questions? Or everybody fallen asleep?
Thanks for that, Dave. Yeah, I've got a fair few questions in here. It might be easier just because there's a few guys who have asked 1 or 2 questions. I know, Neil, you had a fair few, so I don't mind if you want to voice those questions to Dave. And then once you've done, I'll move on to the next guy. So if you're still there, Neil, then feel free to fire away. He might have gone. So if anyone else wants to,
what was did Neil come up with any? What were his questions?
Yeah, I can go through that. So let me just dig these up. What would you say is the most challenging project you have used Alliance on to date, and why? And has this caused you to consider further changes from the original non-valve scheme?
I think probably the most challenging project was the Ennismore Gardens, which you saw there. We're creating that, helping create the basement. And yeah, we noticed that for the design purposes that we weren't taking the corners into account enough. So we did adjust the spacing at the corners. The lances, we have done some work on the lances with different types of valve. And in fact, we've developed one now for short lances that we use a sleeve and that the resin actually comes out at high pressure rather than the low pressure we've got. But it's only high pressure within the lance itself. Once it actually comes out, that pressure drops, and we get even distribution because it's the pressure drop over the distance that causes the problem. If you've got continual high pressure, it will form an even. Well, that's certainly what we found so far. So yes, there have been a few. Anything else?
Yeah, there's a few more. So Neil, off the back of that said, in addition to this, what would you say would be the largest project you have done or the deepest injection you have undertaken? And you've kind of answered some of that.
I think the I think the largest one was again, it was about 250,000, and it was for Eriths, just a little bit more than the Ennismore Gardens one. Deepest we'd been was 27 meters, and that was for Dartford, the London Borough of Dartford, on a housing scheme there. And it was really to try and see if we could find the bottom of a solution feature. We weren't going to grout it to that sort of depth, but we wanted to see if we could drive it, see if we could find out where the bottom of this enormous hole finished. Site investigation couldn't do it, but we could do it with the lances, and we did.
Super. One from John now. What would be the variable cost of permeation system against more traditional underpinning solutions for a housing solution?
Brilliant question. Right. We use standard pricing. It keeps it very, very simple. And this is almost anywhere in the country, really. We'll use a different mobilisation fee, obviously, if we're having to go up to the northwest or northeast. But generally, it works out roughly about, for a 2 metre deep pile, you would have something just over £1,000 per metre length of foundation. So 2 meters of underpinning nowadays would be probably more like 1,500 to 1,600 pounds per linear meter of underpinning carried out. So it's cost effective. And the deeper you go, probably the more cost effective it gets. So if you had to underpin to 3.5 meters, we'd be charging you somewhere round about £2,000 a meter, whereas underpinning would be more like 3.5.
Thanks, Dave. Just going back to another one from Neil here. Would you suggest that lower length lances of circular 2 meters or less would still be more economically efficient than perhaps other methods?
In the right soil conditions, absolutely will be. Yeah, no doubt. From a time point of view, disruption, sometimes, when a house is underpinned, you've got to decant the occupants, dig out floors, do all sorts of bits and pieces. You don't need to do that at all. So from a cost effective point of view, from the disruption alone, very, very much cheaper. And from a carbon footprint point of view, yes, obviously resin is based from oil, but you're using such small quantities. We're using about maximum 10 litres of this material per half metre of lance per metre length of footing. So in fact, its carbon footprint is low.
Brilliant, thank you. Another one again there from Neil. Has there been any testing on nearby coastal areas of soil which is susceptible to water submersion or fully underwater scenarios?
Very good question. I think the answer to that is no. I think my colleague Simon, who lives on the south coast, might know of something. I'm not absolutely sure, but is it affected by erosion? Basically, is one of those things, or salt water. Well, we know from a chemical point of view that it's not affected by even aggressive waters, hydrocarbons, anything, petrochem materials, oil, petrol, anything like that, don't affect it. And it's inert. So it will reduce the erosion that you get. It can't completely eliminate it because it's obviously, we think it's somewhere in the region of 3.5 to 5 newtons per millimeter squared. So if you're looking at something that's having to combat coastal erosion or something like that, it's not going to be nearly as effective as a 40 Newton concrete wall. But it will have significantly more resistance than the undisturbed sand and gravel that you might have on the coast or soils in the cliffs. Yeah.
Brilliant, thanks, Dave. We've got one from Elliot here. How do you prevent heave from the CO2 expansion effect?
It's a good one. Never had that question before. So when you actually see the speed of process here, there's no hydraulic fracture of any sort, not one single particle of soil, once the lance has been driven, gets moved. So the pressures are low. We're looking at between 2 and 3 bar maximum. And it just gently oozes through the soil. When you get the chemical reaction then, and you get the CO2 bubbles generated, it again just gently, I mean, not even that speed, so you don't get any hydraulic fracture. You're not pushing particles out of the way. So the CO2 bubbles don't create heave of any sort at all. They're encapsulated within the grout. And if you looked at that, even under a microscope, you wouldn't see any sort of foam of any sort. The resin has completely encapsulated the soil grains, and it just looks like concrete, basically. Any others,
Super.
Matt?
Yeah, I've got a few more to whiz through. One again from John. What reassurances are you able to provide local environmental authorities for the impact of permeation engineering techniques and avoiding blocking of underground aquifers?
Yeah, great. Again, a really good question. Let's go back to some of the other techniques that are used for um, infiltrating the ground with grout. So in other words, you can do things like compensation grouting, and they did a lot of this when they were running the Elizabeth line through under London, because you've got a tunnel, you've created a void, you've got buildings above it, they're bound to have some effect. So before you do the tunnel, you do what's called compensation grouting, and you force more material into the ground. So in fact, you sort of, it's like a steroid injection, really. You musculate the ground. It thinks there's more load in it than there actually is, but that's done all through hydraulic fracture. So it doesn't matter where the grout goes within a fairly large area, as long as you've forced more material into it, you've created that compensation grouting, that increase in pressure, which then holds additional load. That's the whole idea of it. With this, there's no volume change. So all you've done is taken up the interstitial spaces between the particles, which are either filled with water or filled with air. And so you just exchange those. And so you get no heave, you get no movement of any soil particles at all. So in fact, we find with Thames Water, people like that, we can go quite close to a water main and they know, or a drain, they know we're not going to affect it in any way, shape or form. Great question. I actually never had that one before.
Brilliant. Thanks, Dave. Got one here from Bill Keane. Probably a follow-on to that as well. Is how is the grout designed to resist hydrostatic pressure?
Very good point. Now, if we go back to the Ennismore Gardens example, we are actually asking that treated ground to act as a temporary shutter. So yes, you have to have a look at what sort of capacity it can give you. You're only digging out, as you would normally do, over a sort of about a meter length for underpinning. So it's having to bridge about a meter, but it's also got these things running through it, and they're stuck to it. So these are pretty hefty bits of steel. They're 4 mil thickness, and so they act as pretty substantial reinforcement within that consolidated ground. So you get, and we've done some design checks on it, you get over that depth, so it's about 2.4 meters, a huge amount of resistance from that hydraulic effect of the water being held back. But we do need to check it, and it's done on a temporary works design. Another great question.
Brilliant. Thanks, Dave. Last few on here I've got where the soils are suitable, how does the Lance system compare to new piling?
Well, that's another great question. If you had an open site, it was suitable for either, and you could run a little masted rig to CFA piles. It's going to be a lot cheaper than ours. But if you couldn't get a rig to it, for instance, it was behind an existing building, how are we going to design a footing? We can't really get a rig there. We can install these things to whatever depth you want, really. And you can then build your footing straight on top of it. So that's where it suddenly becomes cost effective. It's if you can't do something another way. So you can't take a piling rig straight through a house if it's a terrace house and work on the extension at the back. You can with this because you just carry the tools through and the resin and you just work at the back. That's where it becomes cost effective. On a new site, very, very unlikely. Unless it's on a slope or you just can't get the equipment there.
Brilliant. Thanks, Dave. Another one here. Are there any health and safety issues associated with the resin reaction when used in confined spaces and basements?
Fantastic question. Right. Remember me saying that the reaction, chemical reaction, releases CO2. Therefore, you will get CO2 in an excavation. So part of the health and safety, safe system of work is that these areas are fully ventilated. So in fact, you force air into them just to make sure that you don't get a buildup of CO2, which obviously sits down. So if you've got anybody going down those holes, yes, they would be overcome, I would imagine, with it. So we do take that into account if anybody is going to go near these things. It's rare, of course, because normally it's under a house. Nobody's actually going to go down under the house. And once the CO2 will just disperse, it won't get caught. But if you've got an excavation next to the area that you've injected, yes, absolutely, we need to ventilate it.
Brilliant. Thank you, Dave. Another short one here from Ivan, who's asked, is the system appropriate for use in chalk?
No. If you think about chalk, it's very like an incredibly stiff clay. If you could drive the lances into it and there were fissures already in the clay, sorry, in the chalk, it's possible that you might actually be able to hit those, and if the fissures were weakening the chalk, create some form of not even consolidation. You're just filling up fissures. It's very like a clay. You can't permeate it. It's so no is the answer.
Thanks, Dave. That someone else did ask as well. For subsidence and sandy clay, can the lance system be used? So that also answers that question, which is great.
While we talk about clays, we've done various experiments and we've worked out that it doesn't work really at all in clay contents more than about 15%. So if you've got a soil sample and it's roughly 15% or less, and you look at the other part of the grading curve, you will get in sufficiently good permeation to create a composite soil that you can rely on. More than 15%, and as you probably know, guys, you end up in little lenses. You're not going to get any permeation into that, and your pile will end up a funny shape. Now that isn't always the end of the story. You look at the load you're trying to take, what it is you're trying to do, and remember that the lance itself, it actually acts as a conduit for load, because where it's sandy and gravelly, it sticks to it. If you've got a little bit of clay, it doesn't. Sand and gravel, it does. And so in fact, the lance will transmit some load straight down to the next layer. So we have found that in fact, in sort of marginal ground with thin lenses of clay, it can work, but again, for pretty light loads.
Thank you, Dave. Just another one here from Esme, asking about your standard warranty period for the repair.
Right. Yeah, we talked about that earlier on, didn't we? About the fact that we can get a defects liability warranty 10 years. It's all you can get on the market. It used to be 12. Our asset guarantee for foundations and structural repairs used to be 12. The market, for whatever reason, have reduced that down, and all you can get, we've got as good a guarantee with the ReFORCE system as we have for standard underpinning, is 10 years.
Brilliant. Thank you, Dave. Got another one here from Veronica. Can you use this system to stabilise Kempton Park gravel under a pad foundation, 1.8 metre squared area, 2 metres deep, before underpinning the pad foundation in quarterly stages?
Now, when she meant in quarterly stages, I guess what we're talking about is in plan, is doing it in a number of, like four corners really. Yes, you can. Kempton Park gravels can have quite a lot of clay in them actually. The majority of the ones we've come across have been absolutely all right, but we've also come across Kempton Park gravels that are quite clay. So what would be really good would be to see the site investigation that you've got, fire us that query for that particular thing, and we'll take a look at it and see whether they think it's a good idea. Again, to some extent, it's the thickness of the existing pad foundation. We've drilled often 2 meters through 2 meters of concrete, and then gone out a meter, 2 meters beyond that to increase the capacity of a pad foundation, and it's worked a treat. And actually, talking about guarantees and things like that, statistically, we've been installing these things for over 18 years now. We have had 5 callbacks, and we've done thousands and thousands of installations. And 3 of the callbacks were wrong site investigation information. So in other words, you rely on the information you're given. We actually found out it was wrong because you go back, because what we'd done hadn't worked, and therefore you go back, you have a look at it, you do our own site investigation. We found out actually it was completely wrong. There was another 4 meters of soft material underneath it, of which you can't inject. It's not the right material. So those 3 were rejected. The 4th one was a partial underpinning of a property. Site investigation was perfectly good. We went and underpinned this section of the house, and then about 5 years later, the client came back and said, "Well, the cracking's still happening." So we went back and we monitored it, and we did our own site investigation again, and actually found out that the part of the house that hadn't been moving was, and that the bit that we'd done was perfectly stable. So because the boundaries were the same, of course, he was starting to see the same sort of cracking happening again. So in fact, out of 5 we've had, we 4 were nothing to do with the technique. The 5th one, however, we overlooked the type of soil. Just, we don't know how it happened. It was early days, and in fact, it wasn't suitable. So we gave the client their money back. So they could put it towards I think they had a screw pile. It was a tiny little porch as it happens, and they did something else. So yeah, that's again sort of the reliability of it.
Brilliant. Thank you, Dave. One here from David Boyce. How do you measure permeability, non-suitability for the system?
Yeah, you can have permeability tests, obviously, but you'd have to have that all the way down the depth that you need to go, and that can be done. Of course, you can put a borehole in, and then you do at various levels. You put water in, and you can see what sort of permeability you've got. And I've certainly done that, but not for this. That's for soakaways. So what we do is we look at the grading curve, and we can, our experience gives us a pretty good idea of whether we're going to be able to permeate the ground or not. So that is the simplest question answer, David, for that. Knowledge. But it's surprising how fine as soil we can get into. We did a job for Balfour Beatty in Birmingham, in Edgbaston. We'd been using the system for fill. They really liked it, and they asked us then, could we stabilise the flank wall of an old listed building that they needed to dig straight down the side of it to 3.5 meters depth to form a plant room. And they couldn't figure out how to do it without stabilizing the ground. They couldn't drive sheet piles in or anything like that. So we said, well, look, we'll do a trial. We'll see whether we can. We don't think we can. The site investigation, the soil's far too fine. I've got a bit of it in the box actually under my computer here. And we looked at it and I just said, I think the chances are pretty remote. They paid us to do a test. So off we went, we did the test. I wasn't happy with the results. They looked at them and said, yeah, I think that'll be fine. And remember that question that came back from how do we design for water pressure and the retain side of it? This was 3.5 meters of vertical dig, maximum 2.4 meters long, for them to be able to dig down, put the reinforcement in, put a shutter up, and pour the concrete to create a basement retaining wall. So in fact, it worked, and I didn't think it would, but it did. And you don't really want Balfour Beatty biting at your ankles if it doesn't. So yeah, a little bit nervous at that time, but no, it worked absolutely fine. So yeah, site investigation, look at the soil.
Brilliant. Thanks, Dave. Just fire through the last few here while we're at it. One from Alex here. How do insurance companies view the technology? Do they still consider a property as at higher risk of settlement, subsidence post-work, and charge higher premiums accordingly?
These are great questions. Right. We are and have been very close to insurance companies and loss adjusters over the 30 odd years that we've been going. And so do a lot of chatting to them about techniques. So when this technique came in, oh, brilliant, fantastic. Oh, look how much money and disruption it saves our clients. Very, very happy with it. However, as I said to you, somebody's been coming along and telling people that they can do the same thing to clay soils, and they can't. And now insurers have realized what I've been saying for 20 years has come true, and they have ditched it. I think all but one insurance company that's still at the moment, and they're doing some experiments, saying, yeah, they're going to stick with it. But all other insurers that we know, and certainly loss adjusters, will not use permeation, polymer injection to underpin a house or any building. I hope that answers the question. So we are still doing them for insurance companies under the right conditions, and I think we probably send back 70% of the inquiries we get as unsuitable.
Yeah, so where I've done that.
Brilliant. Thanks, Dave. On to the last two now. These are really great questions, so thank you all for sending them in. When forming a basement using a LART system, will this potentially create a problem for the neighbour's property to form their basements?
Some outfill, so it drains water away from the wall.
We have actually had that question before on a number of occasions, because you are transgressing into the neighbour's land in essence, and of course it has to there go as part of the party wall agreement. We haven't yet had one that has disagreed to it, and what we've pointed out to them is that it's no more difficult to dig than the ground, and that when they come to dig it, it's not going to cause them any it's not like breaking out concrete, so there won't be a huge amount of vibration or any of that sort of thing, but they will get this sort of stabilized ground in which they're digging. And so far they've all gone, oh yeah, good point, yeah, fine, great, on you go. So it would be interesting to test that in other circumstances, but so far it's all been good. Party wall awards have been granted.
Sometimes
Brilliant, thank you, David. I think we're on to the last one here from Ivan, who's asked, how close can this be installed to drainage infiltration systems?
Oh, now there's a good one. So this would be an infiltration system that is gathering water from the ground, channeling it away from wherever. Yeah, you would want to be. You'd want to be a couple of meters away, I would have thought, absolute minimum. But I'd like to see the circumstances this was in, because I'm not quite sure how you're affecting other things. You know, by doing a series of piles in a line, it's not really going to cause too much problem to water flowing through. So it would be the configuration of the drains in line with the piling. But yeah, I would, to be on the safe side, I'd kind of want to be a couple of meters away. Having said that, I mean, we've done loads where we're literally right next to Thames Water existing clay drains. You keep the drains open. We have them fully inspected first of all, find out if there are any defects, rectify those defects first, in joints or cracks or anything like that. Just make sure. And actually, we have injected right next to an existing drain, and Thames Water are quite happy about it because they know it's not going to cause any forces to break the drain. Yes, it will be encapsulated, but they don't mind that. Or so far, they haven't minded it. So you can get quite close if you know that drainage duct is sealed. It's not a problem. If you're using it to obviously gather water, groundwater, yeah, it'll permeate straight into it, clog it up.
Brilliant, thank you, Dave. I think that's all. That's the last question I had on there. So all that's left to say is thank you for everyone who's attended today.
Yeah, very much, Ingrid, my thanks, and great questions. Thanks so much. One, it meant you're listening. Two, you understand it. And if you're going to take nothing else away from today, it doesn't work in clay. Thank you. And please get in touch with us. Ask us, you know, any sort of queries you've got with a project. Just phone us up, send us an email, something like that, and we're very happy to answer the questions. Take care.
Brilliant, thank you very much, guys. Take care.
All the best. Bye bye.